Hello everyone, welcome to air pollution and stratospheric ozone depletion. Air pollutants and their sources. So air pollution is the introduction of chemicals, particulate matter, or microorganisms into the atmosphere at concentrations high enough to harm plants, animals, and materials, such as buildings, or to alter ecosystems. So the key here is that it's not a pollutant if it's not strong enough to cause harm, and that's generally the definition of most of our pollution. Soil pollution, water pollution. If there's something in the water, something in the air that's present in concentrations great enough to cause harm, then we would consider it a pollutant. Air pollution can be difficult to conceptualize because the atmosphere is a complex global system and it has lots of inputs and outputs. Air pollution can be both natural and anthropogenic. There's that word again that I told you were going to see throughout the course, which anthropogenic means man-made. And the effects of air pollution are often seen long distances from the source or sources of the pollution. So we end up having inputs possibly in one country where the effect actually shows up in another country. That also makes the legislation of air pollution hard. The atmosphere is a global commons. Hey, tragedy of the commons all over again. So science and legislation of air pollution is intertwined with both political and social issues. Air pollution has been hard to regulate for that reason. The Clean Air Act of 1970 identified 6 criteria pollutants that the EPA would monitor and regulate. The 6 criteria pollutants are sulfur dioxide, nitrogen oxides, and if you're not familiar with this little thing right here, that says NOx there. The X means it can be NO or NO2, so nitrogen monoxide or nitrogen dioxide, but we just put NOx because it could be either one of those, and we'll talk about them separately later. Carbon monoxide, particulate matter 10 and particulate matter 2.5, and again we'll talk about the differences between those here in a little bit. Lead and ozone, those are the 6 criteria pollutants, and that means that the EPA monitors and regulates the concentration of those in the atmosphere. Carbon dioxide was not included in 1970 because at the time it was not considered a pollutant. We now know that high concentrations of carbon dioxide do alter ecosystems. The EPA currently monitors carbon dioxide levels, but carbon dioxide is still not listed as a criteria pollutant. And just FYI, on the APES exam, they always throw that one in there because most people consider now high levels of carbon dioxide as a pollutant, and in a multiple choice, they'll throw that one in there to confuse you. 2 other major sources of air pollution that are not criteria pollutants are volatile organic compounds, VOCs, and mercury. You already know a little bit about mercury. We've talked about coal-burning power plants and stuff like that. We're going to talk more about both mercury and VOCs as we move on through this presentation. So let's begin with sulfur dioxide. Sulfur dioxide comes from both natural and anthropogenic sources. The main anthropogenic source is the burning of coal and oil, as we know that coal and oil both contain sulfur as an impurity, and when you burn those 2 types of fossil fuels in particular, you end up with sulfur emissions, particularly sulfur dioxide. Primary natural sources are volcanoes and forest fires. Sulfur dioxide is a respiratory irritant and it is corrosive to plant tissue. If it's corrosive to plant tissue, it's going to probably damage leaf tissue, which would reduce photosynthesis rates. And the reduction of photosynthetic rates means that you could have a trophic structure problem. Sulfur dioxide combines with water vapor in the air to form sulfuric acid. See that chemical formula right there? That's a good one to know, H2SO4, sulfuric acid, which leads to acidic precipitation. So again, if we trace this back, we burn coal or we burn high sulfur oil. The sulfur dioxide is released during the burning process. Sulfur dioxide mixes with water vapor in the air. It forms sulfuric acid, and we get acidic precipitation. Now, I didn't make the specific correlation between acidic precipitation and all the things that causes, but we've been through that before when we talked about water pollution and soil pollution. Nitrogen oxides, or NOx. Nitrogen oxide, NO, is a colorless, odorless gas. nitrogen dioxide, NO2, is a pungent reddish-brown gas. If you're not familiar with the word pungent, it means it has a very strong smell. Primary anthropogenic sources of nitrogen oxides are vehicle exhaust and other fossil fuel combustion. So places that have a lot of cars on the road or trucks on the road are going to have high levels of nitrogen oxide pollution. Primary natural sources are forest fires, volcanoes, and bacterial action in the soil during the nitrogen cycle. Yep, bacterial action actually cause the release of nitrogen oxides and nitrogen pollution. So nitrogen oxides are respiratory irritants. They are a precursor to ozone, and they lead to photochemical smog, and we'll talk more about this when we talk about secondary pollutants. Nitrogen oxides combine with water vapor in the air to create nitric acid. There's another one that you need to know, which leads to acidic precipitation. Again, there's acidic precipitation. And it leads to excess nitrogen in waterways, which of course leads to cultural eutrophication. You should be starting to see at this point in the course that so much of what we do in the second semester is all linked together, especially in our pollution units, because usually when there's pollution, it's not just affecting one, like soil or water, it's affecting both. So especially with release of sulfur dioxide and nitrogen oxides, we have an effect not only on the air, but we have an effect on the soil, and we have an effect on the water. And these all kind of go together to create negative consequences environmentally. Carbon monoxide is a colorless, odorless gas. It's formed from the incomplete combustion of fossil fuels. It is a significant outdoor air pollutant in urban areas due to vehicle exhaust. And it is a significant indoor air pollutant in developing countries where people cook with manure, charcoal, or kerosene stoves without proper ventilation. But it's also an issue in developed countries where gas heaters malfunction. And again, we'll talk more about this later when we talk about indoor air pollution. Carbon monoxide has a greater affinity for hemoglobin than oxygen, which means it actually binds better to the hemoglobin molecules in your red blood cells than oxygen does. So it displaces oxygen in your bloodstream, and it leads to hypoxia and death. You've heard of people killing themselves by inhaling automobile fumes. That's what they're inhaling. They're inhaling carbon monoxide, and it suffocates you because it actually knocks the oxygen off your hemoglobin molecules, and then it transports itself through the bloodstream on your hemoglobin rather than oxygen. And when you don't have enough oxygen, you die. Carbon monoxide at lower concentrations than are fatal cause headaches and oftentimes difficulty concentrating. Carbon dioxide is a colorless, odorless gas formed by any combustion reaction. If you remember when we did combustion chemistry, one of the resultant chemical compounds from combustion is carbon dioxide. And this can be a natural combustion reaction, such as a forest fire, or an anthropogenic combustion reaction, such as the burning of fossil fuels. Carbon dioxide is absorbed by autotrophs during photosynthesis, and of course it's released for both autotrophs and heterotrophs during cellular respiration. Carbon dioxide is a primary anthropogenic source. The primary anthropogenic source is the combustion of fossil fuels, and it is a greenhouse gas that alters climate and affects ecosystems by contributing to global warming. A lot of times people will tell me about disruption of the carbon cycle when they're writing an FRQ, and they're talking about like excess breathing. Excess breathing is not a disruption of the carbon cycle. Remember the difference between modern carbon and fossil carbon. The carbon that you're breathing in and out, that carbon dioxide, was recently in the atmosphere. So you're not really upsetting the carbon cycle by breathing more. Yes, you're breathing out carbon dioxide, but the plants take care of the respiration photosynthesis balance there. So when we're talking about carbon dioxide and global warming, we're really talking about disruption or additional carbon inputs. Just remember that when we're writing FRQs, and please don't tell me people are breathing too much. Particulate matter. So particulate matter, the definition of that is solid or liquid particles that are suspended in the air. PM10 are particles that are smaller than 10 micrometers, and they aren't effectively filtered out by the nose and the respiratory tract. Anything greater than about 10 micrometers, your cilia that line your respiratory tract, they can take care of that. They can get it out and you cough or you sneeze that stuff out. But if it's smaller than 10 micrometers, then your respiratory tract really can't deal with that. And if you remember, think back to the test where everybody had trouble with parts per million and parts per billion. There's that micrometer measurement again. That is something that you need to know. Now, particulate matter 2.5, which is particulate matter that is smaller than 2.5 micrometers, they are particularly damaging. PM 2.5 deposits very deep into the lungs and can cause severe respiratory illnesses, including lung cancer. So the smaller the particle, the deeper it can get in your lungs, because the cilia and the natural and the mucus, the natural ways that your respiratory tract cleans itself, it can't do that with these tiny, tiny particles. Particulate matter comes from the combustion of fossil fuels, particularly coal, oil, and diesel, and biofuels such as manure and wood. Any burning that's producing a smoky fire. If the darker the smoke, the more particulates it has in it. So smoky fires have a high amount of particulate matter. Particulate matter also comes from agriculture, from road construction, and any other human activities that kick up dust. Anytime you're putting dust particles in the air, you're creating particulate matter pollution. Natural sources of particulate matter include volcanoes, forest fires, and dust storms. Particulate matter scatters sunlight, so large amounts of particulates in the atmosphere tend to have a cooling effect on global temperatures. There's always a test question, it was one of the released exams a few years ago, about volcanic activity and what that would do to global average mean global temperatures. And the answer is, of course, that anytime we have large volcanic eruptions, we have a lowering or a decrease in average mean global temperatures, because the particulate matter from volcanoes actually scatters sunlight, blocks it a little bit, and so we have a reduced temperature. Photochemical oxidants. Photochemical oxidants are pollutants formed from sunlight reacting with oxides, particularly nitrogen oxide, but also to a lesser degree sulfur dioxide. All photochemical oxidants are harmful to plant and animal tissue. Tropospheric ozone. Now, we haven't really talked much about the difference between tropospheric and stratospheric ozone. You guys know the layers of the atmosphere, though. So the troposphere is the layer of the atmosphere that is closest to Earth. And tropospheric ozone is a pollutant. Any ozone that is not in the stratosphere is considered a pollutant. Is it the same molecule? Yes, it is. It's O3. But tropospheric ozone is a tissue irritant, and it impairs respiratory function. So there's a saying, and there it is right there. Ozone is good up high, but bad nearby. Good up high means it's good in the stratosphere. That's where we want it, but it's bad nearby in the troposphere. In the troposphere, it's a pollutant. In the stratosphere, it keeps us from getting DNA damage from the sun. Photochemical smog is a mixture of particulates and oxidants. It is formed primarily when vehicle exhaust reacts with sunlight, which is why cities, especially with those with a lot of cars, often have a hazy appearance. And we're going to talk more about secondary pollutants, and we'll talk more about photochemical smog. So there's two types primarily, brown smog, which is that photochemical smog. I'll actually write that in there for you. This is considered the brown smog. If you look, you can see this actually in our own city. If you drive into downtown Dallas, towards downtown Dallas on a hot sunny day, you'll notice that it has brown haze that hangs over it. That's photochemical smog from vehicle exhaust reacting with sunlight. Sulfurous smog is formed when sulfur dioxide reacts with sunlight. And this is in places that burn a lot of coal. This type of smog is the famous London pea soup fog of Victorian times. When you read Victorian literature, or if you study that time period in European or British history, there were these really thick fogs that would roll through London. Well, London is on the Thames River, and the water vapor from the river would combine with the sulfur dioxide in the air from the heavy coal burning, and it would create these sulfurous smogs. And that was those London pea soupers that the literature of the time referred to. Lead and mercury. In the past, lead was added to gasoline to improve engine performance. When it was combusted, it traveled with the wind and was deposited on the ground by precipitation. Lead in gasoline is no longer permitted, and atmospheric concentrations of lead have dropped significantly. Current sources of lead, airborne lead can come from peeling lead-based paint, which creates dust or small chips. Lead is a neurotoxin, so anytime you're breathing it in or ingesting it, you're going to have negative effects. Airborne mercury comes primarily from the burning of coal, and we've talked about this numerous times, so you should know this by now. Mercury is not a criteria pollutant, but it is regulated by the EPA under the Hazardous Air Pollutants Program. Airborne mercury eventually makes its way into the food chain, where it bioaccumulates and causes neurological damage. So both lead and mercury are neurotoxins. Volatile organic compounds, or VOCs. VOCs are organic compounds, meaning they contain carbon, that easily evaporate at normal atmospheric temperatures. VOCs are not criteria pollutants, but they are a major source of air pollution. Most of them are hydrocarbons like gasoline, lighter fluid, dry cleaning fluid, oil-based paints, and perfumes. A lot of things that, if it has a strong smell, if whatever it is has a strong smell, there's a very good chance that it's off-gassing VOCs. Now, something that I didn't put on there, VOCs are actually have a natural component as well. A lot of conifers, pine trees, and I'm actually going to write that down here too. Pine trees actually put out natural VOCs. That piney smell that you guys can smell when you walk through a pine forest, that's a result of VOCs. And they actually, large pine forests will actually create hazy conditions, especially in mountain valley regions. VOCs they combine and react with sunlight to also cause photochemical smog. So they are a component in secondary air pollutant formation, and again, we're about to get to that. Primary versus secondary air pollutants. So primary pollutants are those that come directly from a source, and the source is like a smokestack, it's an exhaust pipe of a vehicle, or it can be a natural source like a pine tree or a volcano. These include carbon monoxide, carbon dioxide, sulfur dioxide, oxides of nitrogen, NOx, particulate matter, and volatile organic compounds. Secondary pollutants are formed when primary pollutants undergo transformation in the presence of sunlight, water vapor, and oxygen. So again, primary come directly from a source, and these are our primary pollutants, right? And secondary pollutants are formed when the primary pollutants undergo transformation. And that's usually in the presence of sunlight and water vapor and oxygen, but sunlight and water vapor are the two biggies. Because sunlight and water vapor are catalysts for the transformation, secondary pollutants are formed more quickly and in greater amounts during the day and in places that are sunny and humid. That's important because test questions can be written around that kind of basis of the knowledge. Which of the following would be most likely to have greater levels of photochemical smog? And then, they can name places. You want to look for a place that is sunny, that's humid. And then, of course, I can think of questions I might like to ask regarding when would photochemical smog most likely be, the greatest amount most likely be created, and you could have something like night and day. It's always during the day because that's when the sun shines. Thermal inversions. During normal conditions, air temperature decreases with altitude. And that's this picture right here. So obviously the bottom part is the surface of the Earth. The surface of the Earth is generally warmer than the upper atmosphere. So as you rise into the atmosphere, we go from warmer air to cooler air. This is the normal condition. The normal condition where the air gets colder with altitude means that pollutants can rise into the atmosphere and then disperse. But during a temperature inversion, which is just this over here, right, pollutants become trapped by a warm layer of air that forms mid-latitude, and that's what I just pointed at. The trapped cooler air down here at the bottom is denser than that warm inversion layer, so the pollutants can't rise up and disperse into the atmosphere. Temperature inversions have contributed to several major pollution events. And when I say a pollution event, that's usually an event that traps pollutants for a number of days and then causes lots of illnesses and, in some cases, death. So the most famous one here in the United States is Denora, Pennsylvania. There is a book on my bookshelf that details what happened. They called this the killer fog. It wasn't really fog. In Donora, Pennsylvania in 1948, 20 people died when pollutants from a local zinc and a local steel plant became trapped by a temperature inversion. Now, 20 people died, but hundreds of others were sickened and ended up with permanent lung damage from this event. There was about 5 days where these pollutants were trapped before a change in the weather blew that temperature, that layer of warm air out of there. The most recent one was in Tianjin in China. It was in 1998. 11 people died when a temperature inversion trapped a whole bunch of carbon monoxide and particulates from coal burning stoves. And again, you guys saw the short film that we showed in class. There's a lot of carbon monoxide and particulate pollution in China because not only do they burn coal for energy production, but they also burn personal coal burning stoves for cooking and for heating. So when you get a temperature inversion like this, it can be quite serious. It kills people. Acidic precipitation. Again, this is probably the second or third time we've talked about it, but let's go through it. So normal rainwater is slightly acidic with a pH of about 5.6. This is about the fifth time I've said that. Fair game on the test. Because carbon dioxide in the air combines with water vapor to create carbonic acid. Carbonic acid is a fairly weak acid, but it does lower the pH of normal rainwater. Acidic precipitation refers to atmospheric water, such as rain, snow, sleet, hail, or fog, with a pH below 5.6. Most anthropogenic acidic precipitation is the result of burning fossil fuels, particularly coal and oil. But it can also be caused naturally from sulfur emissions from volcanic eruptions. So earlier in the presentation, we talked about sulfur emissions from from volcanic eruptions, and that can be a source of acidic precipitation as well, a non-anthropogenic source. Nitrogen oxides, or NOx, that X should be subscripted right there. Nitrogen oxides and sulfur dioxide combine with water vapor in the air to produce nitric and sulfuric acid. And again, this is the second time in the presentation you've heard that. Pollutants released in one location can travel hundreds of miles and damage sites very far away. So national and global control of pollutants is important. In the United States, acidic precipitation and the rates of its damage are improving because of there was amendments to the Clean Air Act in 1990, and those amendments have actually been very successful in reducing the amount of sulfur emissions primarily, which obviously is a large cause of acidic precipitation. So acid deposition can do all of the following. It can lower the pH of surface water, which leads to a loss of biodiversity due to either the direct death of aquatic species. Sometimes the pH drops so significantly that aquatic species just can't tolerate it and they die. But lower pH can also cause reproductive harm in aquatic species in various ways. Mostly it's that the eggs are damaged, and so the young of the aquatic species, the eggs don't survive, or the babies are damaged in some way. It can also cause trophic structure collapse because if there is damage to the phytoplankton or the photosynthetic organisms in the aquatic ecosystem, then if the producers go down, we have trophic structure damage or trophic structure collapse. Acidic deposition also mobilizes the metal ions in the soil, particularly aluminum, and these metal ions can leach into surface waters, which can lead to a loss of biodiversity. Acidic deposition damages plant leaf tissue, which weakens the plants and makes it susceptible to insects or disease. This is a major problem in forests in the northeast of the United States. There's a fair amount of coal-burning power plants in the northeast, and the leaf tissue of forests in the area can become damaged. If the leaf tissue is damaged, then the rates of photosynthesis go down, but it also weakens the entire plant. So then when you have a disease or an insect that comes through, those trees are more vulnerable to that pest. Acidic deposition can damage monuments and buildings, and it can erode painted surfaces such as automobile finishes. Pollution control and prevention. Pollution control involves prevention, cleanup technology, and innovative practices that make polluting processes and industries obsolete. Prevention is the best way to reduce air pollution and all types of pollution, and we've talked about that before. So how do we reduce sulfur dioxide? Well, you can burn lower sulfur coal, such as anthracite coal. However, anthracite is harder to obtain. It's that quote-unquote hard coal, and anthracite is more expensive. You can also do fluidized bed combustion at coal-fired power plants, and we're going to see a graphic on that, and I'm going to talk a little bit more about that. We can also employ wet scrubber technology on smokestacks at coal-fired power plants to reduce sulfur emissions. How do we reduce nitrogen oxides? Well, we can lower the combustion temperatures and make sure we have the correct amount of air and oxygen during coal combustion. Now, this is a tricky process and it's tough to get right, but the higher the combustion temperature, the more nitrogen oxides are produced. So if you lower the combustion temperature and have the correct amount of air and oxygen, you can actually improve the amount of pollutants that you put out. Catalytic converters on vehicle exhaust systems are really important, and they have to be checked frequently for efficiency. When you guys get your car inspected, they're looking at what comes out of the tailpipe. The higher pollutants that come out of the tailpipe, the more you're contributing to air pollution. So catalytic converters help with that. How do you reduce particulates? Well, baghouse filters at coal-fired power plants are important. This is a chamber that the flue gas from a coal-fired power plant goes through, and it actually goes through these filters, and they do look like bags, and it reduces a lot of the particulate matter. We can also use electrostatic precipitators at coal-fired power plants, and again, I'm going to show you a graphic of all these technologies. So how to reduce smog? Evaporation control collars and sleeves on gasoline pump handles. If you've been to a gas station recently, you know that there's these collars at the base of the gasoline pump handle. There's also sleeves on a lot of them where you have to kind of compress the sleeve as you stick it in your gas tank. All of those are evaporation control devices because gasoline is VOC. So that stuff evaporates and it causes it contributes to photochemical smog. Regulations on the use of dry cleaning fluid and lighter fluid for barbecues, regulations reducing the use of wood-burning stoves and fireplaces, the limiting of personal vehicle use to every other day. Mexico City has done this. I think I told you Mexico City sits in a basin. It has very poor air quality and frequent pollution events, and so in order to combat this, they've limited personal vehicle use to every other day. Your license plate determines when you can drive. There's, even numbers on one day and odd numbers on the other. Expanding public transportation networks to limit personal vehicle use. Beijing did this during the Olympic Games. They had a great success with it. If people use public transportation more, then the number of vehicles on the road is reduced, and you can improve air quality. Encouraging carpooling by offering faster HOV lanes in cities. Dallas has HOV lanes where it's 2+, and if you have more than one person in your car and you're commuting, you can take the HOV lanes. Also, charging a toll for road use at rush hour. London does this. London has pretty bad traffic. It's a very heavily populated city. And basically, if you want to drive a personal vehicle with only you in it during rush hour, they're going to charge you a fee to do it. So this encourages public transportation use, which improves air quality. Okay, I told you that I was going to show you pictures of these technologies, especially for coal burning power plants. So this, we're going to start with fluidized bed combustion over here. So if you look at the inputs, here's your coal and here's your limestone. So coal, what happens is there's a hopper for coal, there's a hopper for limestone. Those are combined over here, the coal and the limestone feed. All right, and they feed into this bed area right there. That's that mix of coal and limestone. The air is pumped into that, and this is where the combustion occurs. When you burn coal in the presence of limestone, the sulfur reacts with the limestone. Limestone is a buffer. So we have a reduction in the amount of sulfur emissions there. And then the steam is put out here. And of course, the steam is what we need in order to turn a turbine. We've got the flue ash coming up here. We've got preheated air here. And then we got a fly ash recycling device over here. So this is really the big part of it right there. This is the fluidized bed, and the fluidizing air is coming in from over here from the air intake. and the air is flowing through. Remember, you need a good airflow in order to get good, nice, complete combustion. So the air is flowing through, and you're burning coal in the presence of limestone in order to buffer those sulfur emissions that are coming out. Here's an example of a baghouse filter. It was tough for me to get a good graphic that really showed what was going on. So the crude flue gas input comes in here and it flows over these baghouse filters, right? And as it does that, the particulates kind of accumulate on these filters. Eventually the solids kind of drop out in the bottom here, and there's little escape hatches right here where they clean it out. The cleaned the cleaned flue gas comes out the top here and then can be exhausted out that side. So the dirty air comes in here, flows across these chambers, which are basically filters, and the filters can be removed and tossed and disposed of, and then the solids can be emptied through the bottom here. And then this is an electrostatic precipitator, and again, this is kind of a sideways view of an electrostatic precipitator. So there's a current right here. There's the high voltage source. There's a current that's running through this electrified plate through the middle here, this part right here. So the crude gas or the flue gas comes in through the bottom, and it's run across this plate. And the plate grabs on to the little to the particulate matter there and holds onto it as long as the electricity is flowing. So the cleaned gas comes out here up at the top, and then when the electricity current is turned off, then all the particulates fall down into a collection chamber here, and then they are disposed of. So it's a plate that grabs the electrified plate that grabs the particulate matter that's coming out of the flue gas in a coal-fired power plant. All right, so we just talked about air pollution. Now we're going to talk about stratospheric ozone depletion. They are in the same chapter because they both deal with the atmosphere, but there's not a ton in common. So we'll get to what's in common here in a sec, but first let's talk about what stratospheric ozone depletion is. So the sun emits ultraviolet radiation. You know this. This is why we wear sunscreen. It emits UVA, which is low energy ultraviolet radiation, and UVB and UVC. UVB and UVC are more energetic. Acute or chronic exposure to high amounts of UV radiation causes DNA and tissue damage, particularly those more energetic ones. UVB is particularly problematic. Most of UVC is filtered out by the ozone layer, but UVB gets through in larger amounts. UVB radiation increases the risk of skin cancer and cataracts. It harms the leaf structure and the leaf tissue of plants and the cellular structure of phytoplankton, thereby reducing rates of photosynthesis, and it damages food webs because of reduction in photosynthesis. The ozone layer in the lower stratosphere, right there, absorbs much of the sun's UV radiation, and the ozone layer is essential to life on Earth. Without it, we would all have DNA damage and be burned to a crisp. Yay. All right, so let's talk about how ozone is formed first in the stratosphere. So ozone, and the chemical formula for that is O3, is formed when UVC radiation in the stratosphere strikes a diatomic oxygen molecule. So oxygen floats around in the atmosphere in this form, diatomic, and when it is struck by UVC radiation, the UVC radiation breaks it apart into two monoatomic oxygen molecules. So now we have these two guys floating around, these monoatomic ones. So one of these monoatomic oxygen molecules combines with a diatomic oxygen molecule, and it bonds, and it creates ozone. The newly formed ozone molecule can be broken apart by UVB or UVC radiation, which forms, again, a diatomic oxygen molecule and what they call a free radical or a free oxygen molecule. So this process of the creation of ozone and the destruction of ozone, and the creation and the destruction are both driven by UV radiation. It's a continual process. So up in the stratosphere, ozone is continually being broken down and recreated by the combination of oxygen and UV radiation. And that's what this says right here. Okay? So this is the normal thing. It's broken down, it's created, it's broken down, it's created in a continual process, the interaction between oxygen and ultraviolet radiation in the lower stratosphere. Okay, and this is what it looks like in graphic form. So you've got the sunlight, it strikes a diatomic oxygen molecule, right? And that splits it into two monoatomic. That was step one, right? And then the monoatomics find a diatomic and create ozone, okay? And that's what's going on here. And again, this is a two-way reaction. So the ozone is created, the ozone is destroyed. The ozone is created, the ozone is destroyed, all by the action of UV radiation. So what happens when we have destruction of ozone molecules that's not caused naturally by UV radiation? What stuff is doing that? Well, stratospheric ozone can be broken down by chlorofluorocarbons, CFCs primarily. CFCs are man-made chemicals. There's no natural source of CFCs. There's nothing on the planet that naturally off-gases CFCs. They are man-made. CFCs come from refrigerators and freezers, air conditioning units, the production of styrofoam, and aerosol propellants. Refrigerators and freezers and air conditioning units have to have a cooling unit. The cooling unit uses CFCs. Have you ever heard of Freon? Freon was the DuPont patented name for chlorofluorocarbons. They're refrigerants. The production of styrofoam also uses those, and aerosol propellants. Now, a lot of those have been phased out, but some aerosol propellants still use CFCs. CFCs introduce chlorine to the stratosphere. That's what a chlorofluorocarbon is. It's a chlorinated fluorocarbon. Chlorine attaches to an ozone molecule, forming chlorine monoxide and diatomic oxygen. So here's our ozone molecule, right? The chlorine from the CFC grabs onto that ozone molecule and it rips one of the oxygens off of it. In that process, it creates chlorine monoxide and diatomic oxygen. So it's just destroyed an ozone molecule. The chlorine monoxide then reacts with a free oxygen radical, and it pulls the oxygen from the chlorine monoxide molecule to create another free chlorine plus a diatomic oxygen molecule. Okay, so again, you can see that there's no formation of ozone here, but now we have that chlorine, which is free again. This is problematic because that chlorine molecule that's free can now go back to step one and yank another oxygen molecule off of ozone. So one chlorine molecule can create this cycle over and over and over. It can rip apart 100,000 ozone molecules. One chlorine molecule can rip apart 100,000 ozone molecules. We're going to talk about that more in just a second, but it's a very destructive process. Now, the free chlorine molecule, like I said, is available to go on another ozone killing spree, and the entire destructive cycle continues. And this is what it looks like. So here we've got our step one right here. We got the introduction of, this is a CFC here. This is a CFC. UV radiation breaks the chlorine molecule off of that CFC, right? The chlorine molecule floats around until it encounters ozone. There's our ozone right here, right? And then the chlorine rips an oxygen off of the ozone molecule to create chlorine monoxide and diatomic oxygen. So the ozone's just been destroyed, all right? So here's the next step. Right, oxygen formed, a free radical oxygen combines with the chlorine monoxide to create diatomic oxygen, and it frees up that chlorine molecule to go do this entire process again. And this part right here begins over and over again. We call this the chlorine cycle. Do you have to know the chemistry behind it? You sure do. You might as well memorize it. Thanks. All right, so like I said before, one free chlorine molecule can catalyze the breakdown of up to 100,000 ozone molecules. So even small amounts of CFCs in the stratosphere can potentially be very damaging. Because there's little vertical or horizontal mixing of air molecules or molecules in general in the stratosphere, what gets up there stays up there. So although CFCs have been limited since the early 1990s by the Montreal Protocol, Montreal Protocol was signed in '87, but we really didn't start phasing out CFCs until about 1990. It's going to take a long time to heal the damage that's been done to the ozone layer. Because again, those chlorine molecules are still up there, and we haven't completely eradicated CFCs. They're still used in limited contexts. So the thickness of the ozone layer is measured in what we call Dobson units. The ozone layer is overall thinnest at the poles, both the North and the South Pole, and at its lowest Dobson measurements during polar winters. So why is that? Well, it's dark during polar winters. And this intense darkness, since there's no sunlight there, there's no ozone being made. Remember that it's the incoming solar radiation, the UV radiation, that drives the creation of ozone. So if there's no incoming solar radiation, then we also do not get the creation of ozone. A thinner ozone layer allows for more of the damaging UVB rays to strike the Earth. So why is this bad? Well, it leads to plant tissue damage and decreased rates of photosynthesis, which of course leads to changes in the trophic structure of ecosystems. It also causes increased rates of skin cancer and cataracts in both humans and animals, especially in countries that border the Antarctic. The Antarctic's ozone layer is the thinnest of all the places on Earth, well, above Earth because it's in the atmosphere. It's thin on both poles, but it's thinnest in the Antarctic. I don't like to use the word ozone hole because there's not really a hole. It's just an extreme thinness. And of course, it varies by season. So Chile and Australia have already reported increased rates of skin cancer and cataracts, both in human and animal populations. So let's talk about indoor air pollution. Indoor air pollution is a significant human health hazard in both developing and developed nations, but it's different in developing nations than it is in developed nations. So indoor air pollution in developing countries, usually this is caused by smoky cooking fires that burn wood, manure, or coal as a fuel source. Combined with poor ventilation or no ventilation, this leads to things like carbon monoxide poisoning, the inhalation of particulate matter, which can lead to increased rates of acute respiratory infections, pneumonia, and bronchitis. So cooking with an indoor cook stove that produces particulate matter can also exacerbate tuberculosis symptoms. A lot of people in developing nations are infected with tuberculosis bacteria in their lungs, and their indoor air pollution actually worsens their tuberculosis symptoms. It can also weaken the lungs and make them more susceptible to tuberculoid infections. So even if you don't have tuberculosis, if your lungs are already damaged, then they're prime breeding ground for tuberculoid bacteria. Indoor air pollution in developed countries is a bit different. So in developed countries, people spend more time indoors now than they did in the past, which increases their exposure to toxins in the home. Homes are now better insulated and better sealed, which means the pollutants can't escape and fresh air isn't circulated inside. More products in our homes are now also petroleum-based, and petroleum-based products off-gas more chemical fumes. Sources of indoor air pollution include carbon monoxide poisoning from faulty gas heaters, headaches and mental confusion from volatile organic compounds that are found in paints, pesticides, cleaning products, carpeting, foam insulation, furniture, and pressed wood or particle board in our homes. Cheap furniture is made of pressed wood or particle board, and it has a smell to it. You can smell it when you go into the furniture section of a discount store. Respiratory issues, including bronchitis, emphysema, and cancer from tobacco smoke. Respiratory issues from the inhalation of particulates from fireplaces and wood heating stoves. You wouldn't think that would be an issue, but it can be. Neurological damage from airborne lead paint chips or lead dust. Respiratory issues, including lung cancer from asbestos fibers in ceiling tiles and insulation. Lung cancer from radon exposure. Radon gas is formed from the decomposition of granite. So the problem is most acute in areas with granitic types of bedrock and homes with basements. So as the granite decomposes, radon gas is off-gassed naturally. And if you've got a basement, the radon gas will gather in the basement. And if you spend time in that basement, any amount of time in the basement, you'll end up with high levels of radon exposure. Radon causes lung cancer. Respiratory and immune system dysfunction due to the inhalation of mold spores from wet bathrooms and from moist air conditioning ducts. So sick building syndrome, this was actually on the exam a few years ago. Sick building syndrome is the toxic buildup of indoor air pollutants in airtight spaces, such as newer office buildings. Sick building syndrome can also occur as the result of poorly designed structures that inadvertently circulate heavily polluted outdoor air, such as from a nearby or adjacent parking garage, into the building's air intake or heating and cooling systems. So off-gassing of volatile organic compounds from office furniture, carpeting, vinyl wallpaper, adhesives, insulation, even copy machines can cause eye and throat irritation, nausea, headaches, fatigue, and the inability to concentrate. And guys, we spend a lot of time at work. So when we're in areas that are off-gassing these volatile organic compounds, it can really make you sick if you're spending 8 hours a day breathing that stuff in. The EPA has identified 4 reasons for sick building syndrome, and they are inadequate or faulty ventilation systems, chemical contamination from volatile organic compound off-gassing, which we just talked about up here, hydrocarbon contamination from outside sources transferred through building air intakes, which I talked about up here, and biological contamination from inside or outside, such as mold from wet surfaces or pollen that gets in through air intakes but can't get out because the building is heavily insulated. And here's just a little silly graphic of sick building syndrome. Thanks, guys.